right.
Okay, so maybe we'll start. So welcome everyone. It's my pleasure to welcome Lee Kennard from Syracuse University, and he's going to speak about the non-cyclic, well, not the, sorry, non-cyclic fundamental groups and the Grove Symmetry program. Thanks, Lee.
All right, and thank you to you and Boris for the invitation, and thanks for organizing this Zoom seminar. I can tell that not all of you are in Oregon, so this is really nice to see different faces. Yeah, thanks for coming. So this talk is basically about the fundamental group and positive curvature and symmetry. Some of this is work of my student, Alaha Khalili Samani, who's finishing this year, and my collaborator in Beijing, Yusheng Wang. So the focus, as I said, is on positively curved manifolds, and by that I mean positive sectional curvature. And the question is, what can we say about the fundamental group? So this is a classical, how does curvature impact topology question. Classically, there's very little known, and you know about these from your very first Riemannian geometry class. So the first thing to remember is that pi1 is a finite group. This follows from the Bonnet-Myers theorem, which is really for Ricci curvature, bounded below by a positive constant. Here we have sectional curvature, positive, which is stronger, and we're working on a compact manifold. So there is that K that's strictly positive. So pi1 is finite. We're dealing with finite groups. And then in even dimensions, you have the Singh theorem, which says that that orientability is equivalent to being simply connected. Another way to the consequence of this is that if pi1 is not trivial, then the orientation cover is simply connected. And then, so that means pi1 is either trivial or Z2. So it's still kind of interesting to ask in the presence of symmetry, when do you get non-trivial fundamental group? But, you know, I think it's pretty clear the odd dimensional case is a little more interesting, a lot more interesting. So the main source of examples here, so you have something in mind, are the spherical spaceform groups. These are groups where gamma is a subgroup of the isometry group of the sphere, the orthogonal group. You know, this acts on R2M just in the standard way, and of course the orthogonal group preserves length, so this induces an action on the sphere. And for some finite groups, gamma, this action on the sphere is free. Those are called the spherical spaceform groups. And yeah, so these have, you know, this is a manifold with constant curvature. So the quotient then has constant curvature. So these are a big source of examples. I want to say a little bit about the examples to put some categories of groups in your mind. So of course you have the trivial groups in Z2. These come from the sphere and real projective space. These of course exist in even dimensions as well. A broader class are moving to all cyclic groups. You only have in odd dimensions. These are the lens spaces. Then a broader class still is the subgroups of S3. So S3, you can think of in a few different ways. If you can think about it as the unit quaternions or as SU2. And these groups are classified, and they're, I'll be talking about these a lot actually, but those sort of groups you get here are coming from the geometric groups you have in R3. So you remember probably there's a 2-to-1 double cover of S3 to SO3, and SO3 is the set of rotations in R3. And so subgroups of these are things like the tetrahedral group or the icosahedral group. So if you take a platonic solid and center it at the origin, then some rotations take it to itself. So these are like a generalization of dihedral groups. Those are finite groups, and they're subgroups of SO3. And what you do is you look at the inverse images of those groups, and these are called the binary versions, the binary tetrahedral group, the binary icosahedral group, and so on. So these are the sort of groups you might be thinking about. There's a binary dihedral group too, that's maybe a little simpler. But anyway, this is a larger class. Oh, and it's clear that these act freely on S3 because S3 itself is a group and these are just then a subgroup. So that's, these are not all of the three-dimensional spaceform groups, but these are the ones that are really easy to see that they're free. But yeah, that's a class that actually we'll see come up. In addition, I was just talking about SO3, but those subgroups are not spaceform groups. And so it was surprising when Shankar in '98 wrote down free actions of subgroups of SO3 there was a 7-dimensional manifold with positive curvature on which these act. And for today, it's interesting to note that not only do these groups act freely, but the quotient still has a large isometry group. Generally, when you go from the universal cover down to the manifold, you lose symmetries. All right, you might think about, there's a condition involving the normalizer of gamma to determine which isometries still act on the quotient. And so generally you lose symmetry when you go down to the manifold, but these ones are still homogeneous. In a follow-up project with Grove and independent work of Bazaikin, they found other groups that are not in SO3 or S3. Z6 times Z6 is kind of the biggest in a certain sense, like the most non-cyclic one. This has a cyclic subgroup of index 6, but that's as close as it is to being cyclic. These ones, though, are not homogeneous when you take the quotient. So these exist, but in the context of large symmetry, they're not like as nice as examples. Okay, so what's known? I'm gonna next discuss some results here. And so I've mentioned the only known general obstructions, Bonet, Myers, and Singh. So that was a short story. So what I'm gonna do is add symmetry assumptions and discuss for the rest of today what are some things you can prove assuming symmetry. And this fits into a research program formulated by Karsten Grove in the 90s. So the idea just quickly is to study positive curvature or non-negative curvature or other notions of positive or non-negative curvature in the presence of symmetry and see what you can prove. Then to study those theorems, those classifications, relax the symmetry a little bit, see what other candidates pop up. And then to study those examples and hopefully, hopefully those examples might have good curvature conditions. So that's just a quick overview. I'm only focused today on this condition, so you can forget about that. Steps 2 and steps 3 if you want. So the prototypical condition, if you're thinking about large symmetry, is probably a homogeneous space. So these are points where the isometry group is so large that you can get to any point from a fixed point. So any P and any Q, you can get from P to Q with an isometry. All right. In other words, the orbit of a single point is everything. The orbit is the whole space. And again, I'm just interested today in pi1. So what does this say? So the theorem, this might have been known for a long time, but the only place I know where this is published is in this recent paper of Wilking and Ziller, where they provide a modern proof of the classification of homogeneous manifolds with positive curvature. They show that pi1 is a finite subgroup of S3 or SO3. And I just want to remind you on the previous slide, I said that I showed that there are examples realizing all of these. So this is an optimal classification result. So I mentioned one way to think about homogeneity is that the orbit of a point is everything. that's very large symmetry. If you wanted to dial this down, you might think about the dimension of an orbit. So a smaller group action that has still very large orbits. And specifically, you might want the dimension of the orbit to be big. So the dimension of the orbit. So say the dimension is the manifold dimension minus k. This number k is called the cohomogeneity. And technically speaking, I'm talking about the principal orbits, because they might have orbits of different sizes. But so if k is 0, this means homogeneous. If k is 1, this is this condition that probably all of you have heard about called cohomogeneity 1. But in general, small cohomogeneity means large symmetry. And there's a major result of Wilking in 2006. So this particular condition allows him to classify the homotopy type of the manifold, of the universal cover. But then in addition, he shows, again, thinking about pi1, the result on pi1 is that it's a spherical spaceform group. So it's one of those groups that acts freely on a sphere and linearly. So there's a lot to this, and I just wanted to advertise this. These are two standard notions of what we mean by large symmetry. Any questions before I go on?
Yeah, could you give some kind of in the for the homogeneous examples? Well, yeah, why do you only see SO3 and S3, or is there some kind of reason why that you only get those small dimensional groups?
Well, okay, yeah, it's yeah, my intuition is, I mean, certainly these would be better people to ask, but my intuition about this is that you know, on the sphere, you have lots and lots and lots of symmetry. But as soon, you know, if you think about even a small group, like a cyclic group, say this is acting diagonally, I'm not sure which way I should be doing this, acting diagonally, the isometry group drops all the way from the orthogonal group to the unitary group. And I should have written the dimension as an odd number. Okay, inside there you have the unitary group. The point is, like, to commute with those matrices, you need to drop the dimension, and you should probably do all this with complex number notation. But the point is, like, even for a cyclic group, you lose a lot of symmetry. And so my intuition is that if you go further to an even larger group, the isometry group shrinks even more. And again, the condition that it's homogeneous is strong. And so even the I think it's a much older problem to classify homogeneous space forms. And I would imagine the answer is just this again, although yeah, that must be the answer. Because constant curvature 1, these ones don't come up. So yeah, by this theorem, yeah, these would be the only ones you get. So does that help a little bit?
Yeah, I think that was helpful.
Yeah. I've been confused by this a lot, but again, what I remember is that when you move down, you lose a lot of symmetries. So for today, I'm not working with homogeneous spaces, not anything close, but I'm working with the condition of torus symmetry. So this is a natural assumption for many reasons. For one reason, if you have, for example, small cohomogeneity, this means your orbits are big. This means your Lie group action is a big Lie group, has large dimension. And because every compact Lie group has a maximal torus, and you can bound the rank of the torus by the dimension, there must be a big torus action, a big torus acting. In addition, tori are easy to work with because they're connected abelian Lie groups. These are the best kind of Lie groups. So it makes working with them easy. So this is going to be the condition for the rest of the talk. The example I want you to keep in mind are the lens spaces here. And these have maximal symmetry in the sense that I'll explain right now. So Grove and Searle in 94 proved that the maximum R, the maximum rank of a torus that could act is M. So the dimension is written in this way, and so the maximum rank is M. And this is sharp, and in fact, they also show that if equality holds, then M is diffeomorphic, equivariantly diffeomorphic to a lens space. All right, so there are examples, even with the maximum amount of symmetry, that have cyclic fundamental groups of all orders. So this is different from the situation with homogeneous spaces, where the maximum symmetry is homogeneous and you get a different set of groups, you get a larger set of groups. But so anyway, I want to redirect you and think, okay, maximum torus symmetry means cyclic fundamental groups.
Lee, I'm just gonna comment, you're just talking about odd dimensions here,
Right.
because the result for even is slightly different.
That's right. Yeah.
Yeah, one more space.
Yeah, that's right. They also do the even dimensional case. Yeah. And there you get the complex projective space, but only the simply connected one, not the Z2. Yeah. So see, yeah, Z2, yeah, even that fundamental group is interesting, but I'm just focusing on odd dimensions.
Okay. I'm sorry. So the Fuller and Wilkins theorem is also only for odd dimension.
That's for all dimensions, actually.
All dimension.
Yeah.
Okay, this is what I thought. Thank you.
Yeah. Yep. Thanks. Yeah. There again, the issue is just whether you get Z2 or not for the spaces, and they what they show is that, like, in every case where Z2 action is possible topologically, then in fact you get one isometrically. Okay, so I've mentioned that, cyclic groups appear even for the maximal symmetry assumptions, even with the maximal symmetry assumption for a torus action. So the question is, if you throw away the cyclic groups, when can you expect other fundamental groups to appear? And so what I want to do is phrase this theorem like this. This is a result of Wrong from 05. So if you forget about the cyclic groups, then the maximum symmetry drops. And it's clear from what I had written right here that it must drop a little bit, but in fact, Wrong shows that it drops by half. In addition, the gammas inside S3 that I was discussing before, these realize equality when M is even. I won't spend too much time explaining those examples, but this is a sharp bound when M is even. When M is odd, though, it's clear that this is not sharp because M/2 is not an integer. So once again, it's clear that it must drop a little bit. And in fact, this is a result due to Frank, Wrong, and Wang. This is my collaborator, Yusheng Wang. They showed that, if 2 does not divide M, so if M is odd, then the maximum symmetry drops even more. Again, same story. If you have equality, you can realize examples. There are examples, but if M is not divisible by 3, if this is not an integer, then clearly, again, it must drop. And the question is how much? Well, this is an open question. All right, we don't know how much further the maximum symmetry drops. But here's the guess, and this was first written down in Wang's paper in 2010. I'll explain what else he did in that paper in a second. The version stated here is in a paper of mine. So the conjecture is that it drops to M/P, where P is a prime, and it's the smallest one that divides M. This is kind of a simple-minded guess based on the fact that R must be an integer. But what's not as simple-minded is realizing that there are examples realizing this much symmetry. So if, whatever R can be pushed down to, it can't be pushed any further than M/P. That's the point. I played with the prime number theorem and things and found enough primes and things to write down examples in my paper from 17 of of non-cyclic groups gamma that act in this dimension. So you can see the P showing up. Anyway, it's if you work it out, that's exactly M over P symmetry. So
Lee, can I ask a quick question?
yeah,
Those results by wrong, are they also just for odd dimensional manifolds? Wrong.
yeah,
That first one, odd dimensions.
yeah, yeah. Again, it's actually just vacuously true in even dimensions, because you would just by saying you would have trivial or Z2. So when he's proving it, he
Oh,
will-
okay. Right.
yeah, it's just a different story. Yeah, so he, you might as well assume it's odd dimensional, and that's how these results are written up. Yeah, thanks. Okay, so this is a conjecture. If it's true, then it's optimal. I want to discuss a little bit of evidence for it. So I have the same kind of assumptions. I'm writing the dimension as an odd number in this way. I have TR symmetry, positive sectional curvature. And this blue P is this prime that divides M and is minimal. And so the conjecture stated in a nicer way is that if the symmetry is large, specifically strictly larger than this, then pi1 is cyclic. So large symmetry implies nice fundamental group. So the results from the previous slide show that this is true when the prime is 2 or 3. It's also true. So Wang showed this in the case of constant curvature manifolds. So that was some evidence that he gave in his paper. In my paper, I generalized that to homeomorphism spheres. So, and this is the universal cover being a homeomorphism sphere.
Which dimension are you talking about here? M tilde.
Sure. Yeah. So this is the same M, and this is true in all dimensions.
In all, so no odd dimensions. Okay, sorry. Thanks.
In odd dimensions. Yeah. So same M there, and yeah, in odd dimensions. Yeah. So, yeah, what's a statement that was actually new? Yeah, so you have to, so P equals 2 and P equals 3 were already known. That you have to move up to a point where this is a new piece of information, but that's right. So I put this condition in a different color. So if you restrict the topological type of the manifold, then it's true for that class. That's the point. Another case in which under which it's true is the case where the torus action does not have a fixed point. And here I'm assuming the dimension is strictly larger than a constant depending on the prime. But this is instead of a topological assumption, you might think of this as a geometric assumption. So, again, more evidence, I think. This condition is motivated by the examples, actually. So in the examples, there's no fixed point. So I don't know, at least for, that's what happens in the example. So in that sense, it's a reasonable assumption. What I want to talk about, though, is I really want to advertise is this result with Wang. So we started talking about this, at some point. We were obviously interested in the same thing. We were trying to prove the next case. So P equals 2 is done, P equals 3, the next prime is 5. And what we showed is that it's true about half the time. And it might still be true in the other half the time, we don't know. So this theorem says, P equals 5 in the conjecture. And so I have all these assumptions. Instead of rewriting them, I'll underline. We're throwing away one dimension because we don't know how to do it. Aside from that, we can show that pi1 is cyclic, like we want. Or if it's not, then it's almost cyclic. There's a cyclic subgroup of index 3. And we call that being almost cyclic. What also I want to point out is that this red case is the bad case, and it only happens when M is 2 mod 3. So in particular, if M is 1 mod 3, then the conjecture holds. And if you work out the divisibility assumptions, 2 does not divide it, 3 does not divide it, 5 does divide it. This is equivalent to saying that the dimension of the manifold looks like 49 plus 60K. That's who really cares? But we're excited because this is an infinite family of dimensions for which the conjecture has been verified. This is a new infinite family of dimensions. So yeah, 49. The 49 is obnoxious. That's our smallest dimensional case that's new. And that serves as our base case in the proof. It's over induction, by induction over the dimension. And so dimension 49 is our base case. This is like, we think of induction as a ladder. This is like missing the first 48 rungs on the ladder. You just have to jump. This was the hardest part of the whole proof. And Wang had some really nice ideas to make this work. Yeah, Catherine?
Hey, I just want to ask you a question. I'm sorry, I'm going back to something because just above the statement of the theorem, you've written true if the TR action has no fixed point and M is bigger than or equal to M of P. In your theorem, you said M had to be bigger than, or wasn't it equal to, or R was bigger than or equal to M over P. I just, what does that notation mean, M of P? M is a function of P? Sorry.
Yeah, I just mean a function of P, and it's, I forget exactly, but it's some constant times P squared.
Okay.
Maybe I should have just written that. Yeah.
Yeah, it looks weird. Sorry. And yeah, and I'm interrupting your story about this theorem, which is super cool, actually.
You don't need to see that. Hold on a minute.
Sorry, didn't mean to interrupt. You were on the part about, jumping your ladder here.
Oh yeah. Well, that's the only thing I'm going to say about the proof. I'm not going to tell you about how we jumped up to, but it was a cool idea. I just had a quick remark here. Cool idea that goes back to a nice result of wrong. I'll mention this later. This result of wrong in a different proof that I am actually going to do. But yeah, it's kind of, I don't know. It's kind of ridiculous. I think that the base case is dimension 49. That's like half of the work of the paper. But yeah.
This base case probably, is based on the example, right? So are you going to show this example?
Yeah, sure. Yeah, 49. Yeah, that's right. So S49, I have to write 49 as 50 minus 1. 50 is 2 times 5 squared. So that tells you what kind of, yeah. So, yeah, so you can think of this inside C5 squared.
Yeah.
You should think about the unitary group. Let me just write 25. Yeah, the point is, let's see, inside there, you think about U5 times U5 times U5, like a block diagonal embedding.
Yep.
And then you take 2 different things. So first of all, there's a T5 in there where you take diagonal circle, diagonal circle.
Mm-hmm.
And then there's also inside U5, there's a gamma, which acts freely. So this is a 9-dimensional spaceform group.
Mm-hmm.
And so I'm going to stop writing, but you take this gamma, you look at a diagonal embedding into here, that gives you an action on this larger sphere. It's just taking the direct sum of the representations. So you have the gamma, you have the T5, and if you work it out, the rank of the torus is, so this is our M, 5 squared over 5. These exist, so I'm not telling you what gamma is. It exists, and you can choose a gamma that's non-cyclic. it's a so-called type 1 spaceform group. It's actually, there's just two generators. It's a semi-direct product of two cyclic groups. And yeah, I mean, these, all of these are classified. So this is just coming out of Wolf's book. And that, this trick about, seeing how much of a torus you can get to commute with it is how you build these.
And dimension 49 was kind of the first one when you see some this phenomenon, right?
Yeah, that's right. Yeah, actually, so let's see. Oh, well, there's also 2 times 5 minus 1.
But Lee, isn't the 49 just because of all your conditions? I mean, you need 5 to be the smallest prime.
Yeah,
right?
almost.
So you need to just look at the cases, right, where that can occur, right?
Yeah, I should have written those down. So yeah, there you have 49. I'm glad you're asking. Most people don't want to see what the exact congruence. That's right. There's the 49 mod 60. That's just coming from the conditions, and then there's the 9 mod 60. So there's these are the two families we have. Just exactly based on those conditions. And we assume this is not 9 bigger than so this is, if you trace all this through, we can't do dimension 9, so we do throw that one away. But yeah, so that's why the dimension jumps up so much. Yeah, exactly.
Okay.
Can you say quickly maybe why you can't do dimension 9?
Yeah, it's just so our methods are I call them, the Wilking style high dimensional methods where you want to use a large torus, but in these dimensions, if in the conjecture, let me move up here. So P is the minimum prime dividing M. One of those cases is always when M is just P.
Okay.
Now 2P minus 1 can, of course, that's arbitrarily
Yeah,
large,
I know what
but
this
you
is.
only have a T2 action. It's just not enough to work with.
Okay.
Unless P is 2 or 3. That's, they can do it.
Okay.
But yeah, if already for P equals 5, it seems like you have a T2 on an M9.
So
Yeah.
is there, okay, so out of that, I'm getting you just don't have a big enough torus relative to the period. You just don't have a big enough torus. What's the minimum dimension or minimum rank you need for a torus? I mean, you're jumping all the way to 49. Is there like...
That's right. Yeah, that's because of the divisibility. Yeah, sort of really what you need is enough of a torus so that you can find fixed point components of at least half the dimension of the manifold.
Okay.
If you think about Frankel or the connectedness lemma, that's a critical dimension and a critical dimension for the fixed point components. And for that, you need the precise bound is something like a logarithm of the dimension. You need the torus rank to be at least log n base 2. And there's no logarithm anywhere on this page, but it's just a lucky fact that if you just throw away that one dimension, or erase it. If you just erase that one small dimension, then the dimension is automatically high enough that the rank is high enough that it's log of the dimension.
Okay, thank you.
Okay, very good.
Yep, thanks. Okay, so that's the theorem with Wang. What I'm going to do is go in a different direction here. So we have been only talking about cyclic groups and torus symmetry. I want to think about relaxing the hope. So let's stop trying to prove cyclic. Let's try to prove almost cyclic. And I want to remind you of a major theorem of Wang. This was published in '99 in one of my favorite papers in the American Math Journal. There were a lot of long, what is it called? Journal of Math or Math Journal? This one, whatever it is. So it's really nice because he only assumes a circle action. All right. if you think more analytically about things, this is just assuming a killing field. That's it. And he shows that that pi1 is almost cyclic. So what I mean by this notation, this is just to fit it on the slide. This means that there exists a cyclic subgroup of index at most this W number. And what's implicit as well here is that M shows up. You're considering any manifold M, but this constant only depends on the dimension. So you should be thinking about Gromov's Betti number estimate. Non-negative curvature implies that the total Betti number is at most C of N, only depends on the dimension. It's kind of like that. In addition, this W of N is big, like that Gromov constant. In fact, it's bigger than the Gromov constant. So if you're interested in like bigger numbers. So this, anyway, that's still though, it's a constant that only depends on the dimension. And pi1 is cyclic up to passing to a bounded index subgroup. Okay, so that's the theorem. Now, on the previous slides, we were talking about larger torus actions. And if the torus is big enough, then pi1 is not just almost cyclic, it's cyclic. And so if you're writing a grant proposal, the thing you do is say, well, what about intermediate results? So if you replace the circle symmetry by a larger torus, then torus symmetry implies S1 symmetry. So it's completely clear that you'll get some bound on the index. That bound though now depends on R. So I snuck a little blue R in the subscript there. And the question is like, what can you say about this R? It's clearly, how does the logic go? It's going to be smaller than or equal to that W of N. And as R increases, that's meaning more symmetry. Well, there's fewer manifolds with that much symmetry. So there's fewer fundamental groups that you're considering. So the maximum index of all of those should be shrinking. And more specifically, if you rephrase that earlier theorem, one of the earlier theorems, once R reaches roughly a quarter of the dimension, then this index must have shrunk to 1 because it's known that the group is cyclic in that case. All right, so the problem is, to estimate this constant WR of N for somewhere between the range of N over 4 and R equals 1. I want to give some examples of results along these lines. So the first, I wasn't really thinking about this at the time, but the first is a result from my paper in 17. So if you have a linear assumption on the symmetry where the slope is 1/12, then you can prove that this constant is small, and in fact, it's independent of N. It's just 5. Now, I don't care about the fact that it's 5. I care that it's independent of N. I find that pretty cool. So there's some, this follows from a more general result in this paper, but without anything further, I wasn't able to shrink this slope any. But thanks to work of my student, this is Alaha again, so I'll mention some of her work in a minute. She proved a lemma in her paper that is a really good lemma that allows you, it gives you algebraic conditions that allow you to pass to a subgroup of small index, but with better properties. And you can imagine if you're trying to find a subgroup that's cyclic, that's anyway. If you combine that with this theorem, you can push the slope down from 1/12 to 1/20. Again, the actual constants here and here, ignore, but there is some constant that bounds this index. And again, what's I think exciting about these is that these are independent of N. A question I have is, is this generally true? If the symmetry grows as a linear function of the dimension, do you again get some constant that is independent of the dimension n? I have some evidence for this, but there's a question about finite groups that we can't quite figure out. So, this might be something that is basically already proved if we, find the right person. But anyways, this is a question I'd like to advertise. If you're reading very closely, you probably saw this green assumption. So that's there. That's unfortunate. So I don't think it needs to be there. This is another question, even for this result here, can you get rid of the 1 mod 4? The tricky thing about this is that this isn't just used in one place. You'd have to figure out how to get around it in 2 different places of the proof. And it's used in 2 different ways too. So that's, there's 2 problems to solve there. I think maybe one of those is solved, but let me not say too much about that.
Do you mean in both proofs, for part 1 and part 2, or just for part 1?
That's right. That's right. Used in both. Yeah.
I'm going to explain a little bit about this slope. This is kind of amazing thing that, slope 12, 1 over 12 is here. So
Sure.
What is behind this?
Okay. Yeah, thanks. That gives me a chance to talk about this a little bit. So yeah, in the proof you have your torus action. Yeah, I think you have a torus action, and I've mentioned that not sure if I mentioned this, but you get lots of fixed point components. In fact, a generalization of Berger's result, which appears in Catherine's paper with Karsten from '94, but also due to Sugahara, that there's a co-rank 1 subgroup with a fixed point. And okay, so you have a non-trivial fixed point set of that R-1 torus. And following some ideas of Wilking, there's methods there which allow you to find fixed point components of circles and even better involutions, where these are large dimensional. Now, there's a lot to say here. I'm not setting up a careful induction proof or anything, but basically, an extreme case is where this is so large that you have a codimension 2. And what you can do is that this implies very strong conditions on the cohomology rings.
What do you mean codimension 2?
So I mean the fixed point component.
Fixed point component. Okay.
Yeah. And so that's, you should think of that as big as possible. The codimensions are even because it's coming from a torus action. And so small codimension fixed point set. Fixed point sets are automatically totally geodesic. And these feed into Wilking's connectedness lemma. This was from this paper I've cited now probably 3 times already. This tells you that the cohomology is restricted quite a bit. And
this is the fixed point set of the Z2, right?
Yes.
Okay.
Yeah, and what happens is, so the connectedness lemma tells you that this is, this takes work. I'm not saying this is obvious, but this tells you that this is a homology sphere and that so is this. And what you can do is, that pi 1, I'm kind of cheating here. I'm assuming I'm on the universal cover so that I have the action of pi 1 by deck transformations. And pi 1 acts on M. You can also argue that pi 1 acts on this fixed point component because we've lifted the torus action. Those actions commute. So you get an induced action on the fixed point sets. And it's a classical result that if you have a free, these are free actions on spheres imply that the group that's acting has so-called periodic cohomology. This is like, if you take the classifying space and take its cohomology, it's periodic in a certain sense. And because it's acting on a sphere, that follows. So you get these group cohomology conditions on pi1. You put those together. This particular lemma I'm referring to is from the Frank Rong Wong paper that I cited earlier. I have references in the back. So this implies that pi1 is cyclic. That's the point. The short story is if you have codimension 2 fixed point component, you get cyclic fundamental group, which is everything you could dream of. If the codimension is 4, 6, 8, that's still small. These methods sometimes work in the same way, but sometimes you have to pass to a subgroup to get a cyclic group. The 12 is the first, this 12 reflects the fact that codimension 12 is the first time when these methods really break down. And
Okay.
yeah, and so then what that means is that you can't apply these methods in that case. You have to apply induction instead. And so that yeah, a little computation there says that yeah, that's the first. So in other words, if you want to improve this result, you can figure out how to do this case. That's it's a concrete that's the bottleneck.
So in some sense 12 is index of success for this method. So it's not just, okay.
Right, yeah. And again, we can improve the 12 to a 20 if you're willing to pass to a smaller subgroup. Like there's a trade-off there. But even really 20 is kind of, as far as 20 is really the limit here, because if you move past 20, I don't know how to get a cyclic subgroup of any index. Based on our methods, I believe probably, I mean, it seems close to me. That's why I'm phrasing it as a reason. I think it's a reasonable question, but
Yeah.
Yeah, thanks. Any other questions about this? The slide's a mess. Okay. All right, so I still want to talk about this idea of interpolating between Wrong's circle theorem and the theorems which tell you that pi1 is cyclic. And so what I'll do is I'll shorten what Wrong's theorem says in this special case. So if you increase the circle to a T2, there's got to be some number that bounds the index of a maximal cyclic group. And what is it? Well, I've already mentioned how T2 is a small torus, and I've already mentioned on dimension 9, it's too small to do anything with our methods. So what I'm interested in on this slide is, instead of considering all 9-dimensional manifolds, I want to consider all of those that have special cohomology rings. So I'm going to make the problem easier by restricting the cohomology. And here's an example. Oh, that sort of thing bugs me. I should have double checked. This is a main result of my student's thesis. This has been published in transformation groups. You should go take a look. Transformation groups. So you see the T2 action. I've dropped the dimension to 7. And 7 is interesting for positive curvature people because there are examples here that are not spheres. And so the result here, there's a typo in the result. Yeah, let me cover that up. Oh, that looks, okay, well, you can see that I'm fixing something. Okay, sorry. So this, I'm not even telling you what the notation means. So the assumption is that the cohomology ring with integer coefficients looks like an Eschenburg space. So the Eschenburg, yeah, I got a little distracted with the typo. The Eschenburg spaces are an infinite family of manifolds known to admit positive curvature. And in dimension 7, they're the only known examples, aside from the spheres and the space forms. So the question here is with symmetry, what can you say about pi1? Nobody's classified the actions that connect freely and isometrically on these. Oh, wait a minute, am I getting confused here? You know, I switched the orders of the theorems. This is not the one in transformation groups, although you should still check out the paper. This one is true for rational. I'm sorry. I got a little turned around. The rational cohomology is assumed to be like an Eschenburg space. What that means, an equivalent way of phrasing this, is that the rational cohomology looks like a product of an S2 and an S5. So there's infinitely many manifolds, but rationally they all look like one of those things. Okay, so what about pi1? We want to show pi1 is cyclic. Well, we can't do that, but we can show that pi1 is cyclic if you're willing to pass to a subgroup of small index, and specifically the index is 12. All right, so this is saying something about W2 of 7. Smaller than that would be W2 of 7 manifolds that are rational spheres or rational Eschenburg spaces. So if you like, it's a partial computation of this W2 in dimension 7. Now, the 12 is kind of a bummer. That seems like a big number. But what's nice is that it's sharp. There's examples realizing this on both the 7 sphere and at least one of the Eschenburg spaces. So I mentioned before the 3-dimensional spaceform groups, and I mentioned these binary polyhedral groups. So the biggest and most complicated one is a binary icosahedral group. You should always go to that one if you're looking for an example. This one, so I is the alternating group on 5 letters that has 60 elements. This one has twice as many elements. Now inside there's a cyclic group of order 10, and that's the biggest one. So this is a group where it's a index 12 cyclic group. It's the maximum subgroup that's cyclic is index 12. Now it acts on S3. That means that there's a 4-dimensional representation. You sum that, you get an 8-dimensional representation. Bring that to S7. So you get a representation there. Because there were 2 blocks, you get 2 circles acting. That's where you get the T2. So in the case of S7, this index 12 is optimal. That you can't prove more than that. Similarly, for the Eschenburg spaces, you just take the ordinary icosahedral group. Again, if I could draw an icosahedron, these are the symmetries. Okay, symmetries of the icosahedron. There's 60 of them, and here the maximal cyclic group has order 5. So again, you get index 12. And this example is due to Shankar again. So he proved that, in fact, there's a free action by this group on the normal homogeneous Aleph-Wallach space. It's one of the examples of Eschenburg spaces. And it's homogeneous, as I mentioned a long time ago. And in particular, there's a T2 action. So this 12 is sharp in both cases. Any questions about that before I move on? Okay, so dimension 13 is also interesting And let me just say there's a pair of results there. So these are kind of in reverse order here. So this, in my paper, I was dealing with rational spheres all the time. And I noticed in dimension 13, T2 is just right. You get a cyclic group. So the index is 1. Here's the result, though, that I was meaning to, I should have put this first in the interest of time. So this is the one in transformation groups, now that I've mentioned that. Can't spell it. So this one considers Bose-Einstein spaces and still just T2 symmetry. And so Bose-Einstein spaces are the other family of manifolds known to admit positive curvature in odd dimensions. And this is it. In odd dimensions, you have the Eschenborg spaces, the Bose-Einstein spaces, and the spheres. And that's it. Those are the only ones that we know about that have positive curvature. So from that point of view, it's natural to study this type of question for these manifolds. And the conclusion here with T2 symmetry is that the group is almost cyclic. You have to pass to an index at most 9 to get a cyclic group. Now, I highlighted those larger indices in orange because that's an open question. We don't know if there are examples realizing those. It's even worse. We don't know, nobody knows if Bose-Einstein spaces admit a free action by anything, even a Z2. All right, so, here to find an example, you would need something like a Z2 times Z2, or, a dihedral group would be something where with a index 2 cyclic. But I mean, we don't know if anything acts freely. So let alone with positive curvature and symmetry. That's a question that I don't know has been completely analyzed, but just to put that out there, that's an open question.
Do you mean, Lee, that not even a circle acting freely?
Yeah.
We don't even know if there's a circle acting freely.
That's as far as I know, and I've asked a couple of people. So there are free circle actions on the Eschenborgs, on some of the Eschenborg spaces that give you the 6-dimensional examples. But yeah, you would think like 13 minus 1 is 12. You would think that the Wallach manifold might be in dimension 12 might be a circle quotient of a Bose-Einstein space. But
I think
from what I've heard, that's not known.
Okay.
That, of course, will give you free actions by cyclic groups of any order. But I don't think anyone knows. Okay, I had a quick discussion about the tools that go into these things, but I think I want to leave it here because this is the main result I wanted to highlight for today. And these questions, this really blows my mind. People have been studying Bose-Einstein spaces since what was it? Sometime in the 90s, I think, when they were written down for the first time. And anyway, so I'll leave it there, and I want to thank everybody for coming and thanks for the chance to speak here.
Thank you, Lee. Does anybody have any more questions?
Besides, obviously use lots of group theory, non-trivial, but what else comes into this story? Say in this your last theorem.
Sure. Yeah, so that's a great question. So I have a slide for that. Let me just quickly say a lot of I already mentioned about positive curvature and torus actions. There's a lot of kind of general theory there. There's these methods from Wilking's paper by induction and using the connectedness lemma. One of the things that one of the reasons why I was able to prove some things was so I studied this connectedness lemma and what it implies. And there's results there using cohomology operations where you can improve this periodicity that you get in the cohomology. And there's still, I have a question about these things. This is related to Adam's original verification of the Hopf invariant 1 problem from 1960. These so-called secondary cohomology operations were defined and developed in his 60 or 80 page paper. And then the proof of the Hopf invariant 1 problem takes a page once he has these tools. So I was able to use this so this is totally like algebraic topology. You have a cohomology ring, you have the action of the Steenrod algebra. I think, yeah, in this paper, I state the question that's still open.
Yeah, so just make sure I understand. So this number 4. So if your manifold has positive sectional curvature and this dimension, and assuming then M tilde is a rational homology sphere, right? This is what is the statement. All right.
Yeah. I don't mean to. Oh, sorry. I just want to jump in because this then is, in the context of the proof, you're middle of the induction step and you have all this stuff like that's used to show that the universal cover is a rational homology sphere. Yeah.
Okay, that's and this is done in particular papers, right? So it's
yeah, this basic strategy. So this is one of the places where this dimension assumption that I was mentioning is used to get that it's a rational homology sphere. And that's using the connectedness lemma, this stuff about periodic cohomology. That's kind of half of what you have to do. And then the other half is to see what that means about pi 1. And I just want to advertise something. So Darren Long and Daryl Cooper, I should put Cooper first. They're both at UCSB. I was a postdoc there at the time, and they told me that if you have a 3-dimensional manifold, which is a rational homology sphere. So this was close to the sort of thing I was dealing with. I had a rational homology sphere. And I asked them, can you say anything about what kind of action groups can act freely on a rational homology sphere? There must be conditions. They said no. For any finite group, they constructed a 3-dimensional rational homology sphere on which it acts freely. So, I was pretty upset when they told me this because I thought this would tell me something, and it doesn't. However, they helped me a lot by telling me about a result of, this is Jim Davis at Indiana and Shmuel Weinberger. In these dimensions of the form 4K plus 1, if the manifold is, I meant to say a rational homology sphere in these dimensions, then this, you can almost forget about that assumption. Then there are obstructions. And so the theorem here is that if pi 1, or if any group acts freely on a rational homology sphere in dimension 4K plus 1, then the group factors as a Z2, Z4, Z8, something like that, times a group of odd order. Now, if you're trying to show that pi is cyclic then, and you show that this is cyclic, of course, then the product is cyclic. That does the rest of the work for you. So this totally simplifies things because you can just study gamma now. Gamma is a group of odd order. if you know anything about groups, you know that groups of odd order are way simpler. If you think about like actions by groups on manifolds, if a group has odd order, then everything in that group is a square of something else. And in particular, everything in that group preserves orientation. That's presumably a nice thing. There's similar such things that happen for odd order groups that make things easier. So I'll just put this at the bottom. This was one more lemma. This is from this 2020 paper. This is a beautiful obstruction, and yeah, it tells you something about, it's telling you something about odd order groups. That's really nice. So for a positively curved manifold with circle symmetry, there's a certain statement about cyclic subgroups. And it's a statement of the form, you know, it's a statement telling you gamma is almost cyclic. That's the point. If you know the index of the maximal cyclic group is small, that's the content of this theorem.
It certainly gives the answer to my, so it's lots of things goes into this.
Yeah, sure. My favorite thing to advertise is that one of the papers I got to cite was a 1900 or 1905 paper of Burnside. I'm sure I could have found it in a book, but it was kind of fun to cite a paper that was that old. Yeah.
So.
Yeah, thanks for your question.
How often in these cases, some of these different theorems, maybe by the edge cases or something, do you get some information also about what the universal cover would have to be? Or is maybe the other way around, that you're mostly putting in information about the universal cover?
Yeah, and yeah, good question. Yeah, both yes to both. So, yeah, in small dimensions where we just don't have enough torus to work with, then yeah, we just put in the conditions on the universal cover. But for the larger dimensions where we can play, where these games work, then we still don't always learn about the manifold itself. But often the proof goes by showing that pi1 of this manifold is the same of pi1 of this submanifold. And then we forget about that manifold and we study this one, and we show that its universal cover is a sphere, a rational sphere, and then we show that its pi1 is nice. The original manifold we don't learn very much about at all.
So, but you get some special submanifolds essentially that you can.
Yeah. The typical thing is like there's a submanifold which has the same pi1, and its universal cover is a sphere or a rational sphere.
Okay,
yeah.
Great. Thanks.
Yep, thanks.
Hi, so I have two quick questions. So in the previous slide, where you have two results.
Let me, oh, no.
This result on 7 manifolds, right? So you get the rational type of the sphere of S2 cross S5, and what about S3 cross S4? Is it that different, or?
Oh, well, that's a good question. Yeah, I don't know. We were thinking, let me think though.
I feel like it's not that different, like rationally to S2 cross S5, but I don't know. I have no idea what you use.
Yeah, actually, oh, I'm being recorded, so I don't want to say, but I think it's true in that case. Yeah, so proving the upper bound of 12, from what I remember, just uses the fact that the total Betti number is small. Yeah, I guess, you know, I didn't even think about that manifold, for example, because we don't know if anything like that has positive curvature. And so as far as proving that the 12 is optimal, you know, you'd have to come up with a new manifold first. Yeah. But yeah, the methods generally, well, this really uses in an important way the cohomology structure, but like for the sphere and this result, we're just using that the total Betty number is small. This tells us that the fixed point sets are also cohomologically small, which is good for inheriting actions by subgroups.
I see. I guess the next type would be like S2 crosses 2 crosses 3, but then the Betty number grows, right?
Yeah, S2 times, yeah. Oh, S2 times S2.
And you don't have any examples. So.
2, 4, 8. Yeah, again, I'll say I think because I'm being recorded, but if I'd be a little more confident otherwise. I think actually, yeah, there too, but eventually big enough Betty numbers, like the proof won't work. I forget exactly where that cutoff is, but yeah.
Okay, thanks. So my other question is about, so you have this slide with the 49 showing up.
Oh, 49. I never get questions about 49. This is great.
So I remember you wrote a T5 at some point in that slide, right? Where the cyclic conjecture in this block, you have this T5. So is this T5 related to the T5 you get in your work on the Euler characteristic with Burchard and Michael? Or?
I'm pretty sure not. I think this is just a coincidence that we're working with. The 5 is really this 5.
Okay.
Yeah, in that case, the 5 comes up because that's just like the best we could do.
Right.
And as far as I know, there's no, I mean, I guess having T5 symmetry would tell you something from that work.
Yeah, except your T5 symmetry with Wilking, that's in even dimensions because you're looking at positive Euler characteristic. You're not looking at odd dimensions there.
Yeah, that's what we talk about in talks. There's results for odd dimensions too, but you have to assume something like equivariantly formal, or if you assume something like that, oh, T5. If you upgrade a little bit more to a T7, and you have an equivariantly formal action, this means a fixed point set has this same total Betty number. Then you can say that the universal cover is a rational sphere. That would be similar to the sort of stuff I've been talking about here. I really haven't explored, like what that. Yeah, there's probably something there. I don't. Right at the moment, I'm not sure of like the strongest thing to say.
Thank you.
Yeah, thanks.
Any other questions for Lee?
Just a comment about recording. I usually actually forget to start recording. This time is actually special. So now, so I would like, so if you would like to get recording, I mean, the speaker, I will give you a link. I will just send you a link. But usually I do not kind of distribute this anywhere. So it's a seminar which gives us freedom to talk about anything we want. You know,
it's a secret recording.
Yeah.
well, it's
only we will be witness to any mistakes you might make.
oh yeah. Okay.
Blackmail you that way,
just to clarify, because
sure.
my attempts to share this with people we're not so successful because usually speakers do not want for this. When they would get recording, they would say, well, okay, I'm sorry, guys, I don't want for this to be posted anywhere. So,
Oh, I see. Yeah.
so that's, I personally don't like any recordings I do by myself. Just, so anyway, but thank you so much for your interesting talk, and that's interesting direction. Lots of different mathematics at the same place. That's always interesting.
Okay. Yeah. Thank you for having me, and thanks everyone.
Please, if you would like to kind of stay with the seminar, please do. It won't take too much time. It's actually quite international, and there are only two people from Oregon here. Everybody else is from other places, as you may.
Not that that's necessarily a bad thing. So it's
yeah, it's I mean, right. Okay.
We're weeping. There are only 2 people from Oregon.
Yeah. Yeah. So this is new reality, which I believe it's not the worst one. I think we have something I would like to keep after the whole nightmare will be over, this seminar. And I hope you guys will support this. And please stay with the seminar if you have time and energy, and we'll be happy to see you again. As well, we actually have scheduled the talk of your institute, and I hope you will show up here to support her. So this is always important. All right. Thank you very much.
All right. Thank you.
And,
Thank you, Lee.
Thanks.
Really nice
you.
talk.
yeah. See you next
All right.
week.
Bye-bye.
Thank you.
Bye.
Bye-bye. All right. Okay.